Okay, so let's talk about inverse trig functions. So you may or should remember from college algebra that functions are inverses. So f and g are inverses of each other if, first off, f composed with g of x always equals x, and g of f of x always equals x. So the functions need to cancel each other out. They have to both be 1-to-1, and their graphs will be reflections of each other across the line y equals x. So maybe the graph of f maybe looks something like this. Then the graph of g would look something like this. And right through the middle here would be the line y equals x. So maybe this is f and g, and they're both 1-to-1. So, like if we had, I don't know, f of x equals 2x minus 1, then you remember how to find an inverse. First, you check and make sure your graph is 1-to-1. That graph is a line. That passes both the vertical line test, it's a function, and the horizontal line test, it's 1-to-1. It has an inverse. Then define that inverse. You would rename f of x y. Swap x and y. So all the y's become x's, all the x's become y's. And now we solve for y. So we'll get x plus 1 equals 2y. Divide by 2. Oops. And then we rename this guy here. We could call him f inverse of x is x plus 1 over 2. And we could put his graph here. If we write him in more like slope-intercept form, has a y-intercept at 0, 1. Right there. Has a slope of 1/2. So if I go over 2, up 1, I get another point. His graph would look kind of like that. Oops, I kind of missed. So this was f. This is f inverse. And right down the middle is the line y equals x. And we could check and see that we, in fact, do have inverses. If we compose them, we need to check two things. We need to check that composing them this direction gives me x and the other way. So if I do that, if I take this guy here and plug him in right there, take all of that, plug it into the x, if I find f of f inverse of x, f says take twice your input. My input is all of this. Then subtract 1. These 2's cancel. I get x plus 1 minus 1. I just get x. That's what I'm supposed to get if they are in fact inverses. And then I'm supposed to check that the other way. Making this guy the outside function and taking all of that and plugging it right there in that x. So that would be input, all of that, plus 1 all over 2. 1's cancel. I get 2x over 2. I do in fact get x. Because I got x, when I compose these both directions, that proves that these are in fact inverses of each other. This guy and that guy. And then you may recall from college algebra, when you did the same thing, would say, I don't know, g of x equals x squared. And so you go through the trouble and you go, okay, well, y equals x squared. swap x and y. And so x equals y squared. Solve for y, so I got to get that y by myself. And the thing most people do is they just go, oh, well, take the square root of both sides, and they write that, and then they'll write this here. And they'll say that these two are inverses of each other. And they'll go to check it and say, oh, well, g of g inverse of x. Take this guy and plug him in there and say square root of x squared. That does in fact equal x. That's what we're supposed to get. If these are inverses, they should undo each other. Square rooting's the opposite of squaring, right? And then they'll write this here, going the other direction. Now we're taking this and plugging it inside here. And they'll say square root of x squared. And they'll say equals x. And that's wrong. That's not true. Square root of x squared is not x. It's the absolute value of x. And you're thinking, whoa, square root of x squared, they just cancel out. No, they don't. Think about this. What if x equals 3? Then the square root of 3 squared would be square root of 9. 3 squared is 9. And I got 3. They did just cancel out. But what if x is negative 3? Then the square root of negative 3 squared. Negative 3 squared is also positive 9, and square root of 9 is positive 3. I didn't get the same thing back. I started with this, and I got the positive version of that back. This function right here doesn't spit out x, it spits out the positive version of x. Oh, that's just absolute value. The problem was at this step right here. When you take the square root of both sides, you're supposed to put a plus or minus. These are not inverses. Square root of x is not the inverse of x squared. X squared looks like this. That's not 1-to-1. That does not have an inverse. It's not 1-to-1. Only 1-to-1 functions have inverses. Square root is not the inverse of x squared because x squared doesn't even have an inverse. So what you did in college algebra, you should remember this problem. You did this thing where you call restrict the domain, or we call restrict the domain. The problem with x squared here is he's got these two arms and he fails the horizontal line test. A horizontal line here hits it twice. We could fix that if we just didn't use the whole thing. Remember, when somebody hands you a formula, they're supposed to also tell you what domain to use. If they don't, you use what's called the natural domain, the biggest domain of real numbers, biggest set of real numbers that makes sense in the formula. So if somebody just hands you y equals x squared, you just assume they mean all real numbers for the domain. Doesn't have to be. A different domain will give us a different function. So I'm going to call this new guy, maybe we'll call him g of x. He's x squared. But on this restricted domain, I only want half of the graph. My entire function is here. I only took that right arm. This is 1-to-1. It passes the vertical line test, so it's a function. It passes the horizontal line test. It's a 1-to-1 function. This has an inverse. 1-to-1 functions have inverses. And guess what that inverse is? It's square root of x. This is g here. His inverse would look like this. There's g inverse. But that wasn't my only choice. I could have said, let's take this new guy. I got to give it a new name because it's a different function, x squared, on this domain, negative infinity to 0. Now I only want to use the negative x's. That guy. He's 1-to-1. It's a different function. It's got a different graph. I'm using different inputs. It's a different function, but it's 1-to-1. It has an inverse. And guess what his inverse is? It ain't square root of x. His inverse is negative square root of x. That looks like this. Here's h. Here's h inverse. See, the problem comes, like I said, right here. When you take the square root of both sides, you're supposed to put a plus or minus. So here's y equals x squared. The inverse, if you're just naive about it, would be this guy, x equals y squared. The problem is this guy ain't a function. That fails the vertical line test. So we can only take half at a time. If I take this half of the original, I get this half, and that's his inverse. If I take that half, I get that half. Now, why do we care about all this? Because our trig functions are not 1-to-1. Consider this guy, y equals sine of x. We know what his graph looks like. Just quickly sketch out a little bit of it. You know this goes on forever and ever. And maybe we'll put a few numbers on here. Here's 2 pi, pi over 2, 3 pi over 2. We could keep labeling this as long as we want. That's not 1-to-1. Like, say, for example, I wanted to know where, for what x values, does y equal, where does sine equal a half? We know that that's at our 30 degrees. At, like, one place is pi over 6, right here. There's a half. But here's another one right there. That's 5 pi over 6. And here's another one here. That's that one plus 2 pi. That's pi over 6 plus another complete time around the circle. And here's another one. That's 5 pi over 6 plus a 2 pi. And then there's another one here and another one here. Here's one. Here's one. They're an infinite number of places. This guy is so much worse than x squared. X squared is what we call 2-to-1. This guy's infinite to 1. For every output, there's an infinite number of inputs. So I can't just go backwards. If I wanted to go, oh, well, if I know this side is 1/2, what does x have to be? I don't just get one answer. And that's what we want in an inverse. We want something that only spits out one answer. So what we have to do is the same thing we did with x squared. We have to restrict the domain. We want to pick some section of this graph y equals sine of x that is 1-to-1 and covers my entire range. And just like with x squared, we got a bunch of different choices. Like, there are literally an infinite number of ways I could define the inverse. But the standard way, the way your calculator does it, is to take this chunk right here. From negative pi over 2 up to pi over 2. That blue chunk right there. Let's graph him by himself. That goes from -1 up to 1. That ain't sine of x. Sine of x goes on forever. This is a new version of sine of x. So maybe we'll call it f of x equals sine of x on this new domain, -pi/2 to pi/2. A function is determined by its formula and its domain. If you change the domain, it's a different function. This is not regular old sine of x. It's this new version of sine with this restricted domain. This guy is 1-to-1. We can look at the picture. It passes the vertical line test and the horizontal line test. So it has an inverse. That says inverse. So we'll define y equals inverse sine of x. That does not mean 1 over sine. That is not an exponent right there. We already know what 1 over sine is. That's cosecant. This ain't cosecant. This is inverse sine, and it's defined to be y equals inverse sine of x if and only if sine of y equals x. If they undo each other. Okay, this is a function. We could graph it. It's going to go like this from -1 to 1. On the x-axis, and from -pi/2 up to pi/2 on the y-axis. And it goes like this. Or a better picture of it, it goes more like this. Oh, that's not cooperating. There's what it looks like. That's inverse sine, also known as, aka, arc sine of x. That's just a fancy name for saying inverse sine. So his domain, anytime you talk about a new function, you want to talk about domain, -1 to 1. His range, -pi/2 to pi/2. Exactly swapped from sine. Here's sine, this version of sine, there's his domain, and his range is -1 to 1. A function and its inverse just swap domain and range. They swap x's and y's. So, sine of x, you give him an angle. X is an angle in specific places. You can't use any angle you want. You want an angle between -pi/2 and pi/2. So that's quadrants. If we were thinking quadrants, that's quadrants 1 and 4 right here. So backwards to -pi/2 up to +pi/2. -90 degrees to +90 degrees. You give sine an angle and it will spit out a fraction. That's what sine does. It spits out fractions. Inverse sine, arc sine, does the exact opposite. You give it a fraction between -1 and 1, and it'll spit out an angle in quadrants 1 or 4. And when I say quadrant 4, I mean a negative angle in quadrant 4. Not like 330 degrees, 11 pi/6, but like -pi/6. So this is not regular old sine. It's a restricted version of sine who has an inverse. So, like for example, sine of pi over 3 is, we know this, root 3 over 2. It's a unit circle angle. You know that. That's in the correct area. That's in quadrant 1. I'm allowed to do it. Inverse sine of root 3 over 2 says, okay, let's look at our unit circle. Let's only look in quadrants 1 and 4. Not everywhere, because this really, where does sine equal root 3 over 2? There's an infinite number of places where that it equals that. I only want the ones that are here or here. So if you look at your unit circle, only here or here, where does sine equal root 3 over 2, question mark. The only place it does that is pi over 3. Okay. What about cosine? So if we look at y equals cosine of x, his graph, we'll get through cosine and tangent much quicker now. His graph looks like this. Here's negative 2 pi. Not 1 to 1, doesn't have an inverse. There is no such thing as inverse cosine for the entire function cosine, because cosine doesn't have an inverse. We want to pick some restricted version of cosine, and the standard section to pick is right here. This little blue section here up to pi, that is 1 to 1. So we're going to take this function, f of x equals cosine of x, on this restricted domain, 0 to pi. That is 1 to 1. It looks like this. That's my entire function. It's on this little tiny chunk. That has an inverse. And his inverse is cosine inverse. That does not mean cosine raised to the negative 1. That is not an exponent. Also known as arc cosine of x. And it's defined by, this is the definition, y equals inverse cosine of x if and only if cosine of y equals x, if these two undo each other. And his graph, the inverse cosine, he's going to have, let's talk here, that guy, that's his domain of cosine. His range is negative 1 to 1. So the inverse is just going to swap those. His domain will be negative 1 to 1, and his range will be 0 to pi. So domain negative 1 up to 1, range is 0 to pi. His graph kind of looks like this. That is also a 1-to-1 function. If a function has an inverse, both he and the inverse are 1 to 1. And finally, tangent. We know what tangent looks like. We got all these asymptotes. It looks like this over and over again. Here's negative pi over 2 to pi over 2. Again, not 1 to 1. We want to pick some section of it that is 1 to 1. Well, the obvious choice is just pick this section right here. So we define this brand new function. It's not tangent. It's a restricted version of tangent. Tangent of x on negative pi over 2 to pi over 2. Not including the endpoints, because tangent's not defined there. So this guy here, his entire graph only lives between these two asymptotes. That's 1-to-1. His domain is negative pi over 2 to pi over 2. His range is all real numbers, negative infinity to infinity. Then his inverse, tangent inverse of x, also known as arctangent, is defined by, they undo each other, y equals inverse tangent of x if and only if tangent of y equals x. And by tangent of y, I mean this version of tangent up here. His graph looks like this. He's got a neat graph. Goes from negative pi over 2 to pi over 2 on the range, and has domain all real numbers. He's got these horizontal asymptotes instead of vertical asymptotes. So his domain is all real numbers, but his range is finite. Arctangent squishes the entire real number line down into a finite region. Okay, so what's important is where we're allowed to use these inverse functions, where they're defined, where the original trig functions are defined, and so forth. So sine and tangent are these two. And when I say here, I mean negative versions of these angles. Cosine is these two, quadrants 1 and 2. Nobody uses quadrant 3. And I'll build a couple more videos where we go through a whole bunch of examples. These are just our definitions, and that's a good